Okay, welcome back everybody, and we begin our discussion of blood filtration, one of the first processes in cleaning the blood that comes to the kidney, um, by essentially describing a process that involves both hydrostatic and osmotic components. The movement of fluid that comes from blood flowing through the glomerulus across the filtration membrane is described as filtration. The filtrate is simply the stuff that passes through the filtration membrane, and those are essentially molecules that are below a certain molecular weight. Remember that they have to cross the endothelial cells, the basement membrane, and also the podocytes that wrap around the glomerular capillaries. The pressure difference is what forces the filtrate across the filtration membrane, working in concert with the osmotic pressure that exists both in the blood and also in the filtrate itself. The renal fraction is the portion of the total cardiac output that passes through the kidneys, and it varies between 12 to 30%, average about 20%. Renal blood flow rate is about 1,200 milliliters a minute, and renal plasma flow rate is simply the renal blood flow rate times the fraction of blood and that is the plasma, and that works out to about 650 milliliters per minute. The filtration fraction is the part of the plasma that's filtered into the lumen of Bowman's, and that's about 19%. And the GFR is the amount of filtrate produced each minute, and that averages about 180 liters daily. The average urine production is about a tenth of that, so most of the filtrate gets reabsorbed, in fact, a considerable amount of it. And this is really a remarkable feat of engineering on the part of the kidneys. When you consider they're about the size of a bar of soap, and they filter 200 liters a day of body fluid every day, you can appreciate that over time, eventually, you start to lose a little bit of kidney function simply due to the wear and tear on the nephrons. What you're looking at here is just a table. This is 26.2 in your text, and this is simply a recounting of the renal blood flow rates. Okay, so um, go ahead and sort of star this. The thing that's most impressive is the amount of urine that's produced from all of the fluid that's filtered. Okay, about a 1/100th reduction in the amount of total fluid volume between the fluid that eventually passes through both kidneys and the urine that's produced. Remember that the filtration membrane represents a three-tiered barrier to prevent large components in the blood from entering the filtrate. We don't want to have protein or formed elements manage to make it into Bowman's, and that's what the endothelial cells, basement membrane, and podocytes ensure. Um, Essentially, what we have to appreciate about Bowman's is that anything below a certain molecular weight will manage to cross these three layers. The fenestrated endothelia, basement membrane, and the pores formed by the podocytes are going to set up certain restrictions on what can and can enter the filtrate. Albumin and small hormonal proteins enter the filtrate, but this is a very small amount. These are reabsorbed and metabolized by the cells in the proximal tubule. Very little protein is normally found in the urine. In fact, if you're spilling protein in the urine, it generally means there's a defect somewhere in the filtration membrane. There could be a mechanical problem, there could be some other type of pathology. The filtration pressure is just the pressure gradient that's responsible for driving the fluid into Bowman's. It forces the fluid from the glomerular capillary across the membrane into the lumen of Bowman's at the rate of about 10 millimeters of mercury net filtration pressure outward. Okay, and this is one of the reasons why we have to have a certain amount of hydrostatic pressure in order to generate any filtration at all. Forces that affect the movement of fluid into or out of the lumen of Bowman's include the glomerular capillary pressure, which is simply the blood pressure inside the glomerulus. This comes from the pumping action of the heart. It's also due in part to the differing diameters of the afferent and efferent arterioles that lead into and out of the glomerulus. The capsule hydrostatic pressure is simply the pressure of the filtrate that's already in the lumen. So that's going to act opposite the net flow of filtrate out. The blood colloid osmotic pressure is the osmotic pressure of the dissolved solutes in the blood plasma, and that's going to be a net filtration pressure into the glomerulus. Um, Remember that large proteins are not going to be able to cross in addition to formed elements. So this favors the fluid movement into the capillary from the lumen. Remember that this osmotic pressure is greater at the end of the glomerular capillary than at the beginning because of the fluid that leaves the capillary and enters the lumen. So when we end up computing the net filtration pressure, we get about 10 millimeters of mercury into Bowman's. Okay, and you can appreciate that in this diagram here, showing you essentially how it is we drive solutes into Bowman's. Okay, so the glomerular capillary pressure, the capsular hydrostatic, and the blood colloid osmotic, as well as the filtration pressure, all end up producing a net force of 10 millimeters of mercury into Bowman's. One of the things we have to appreciate is that if we perturb this at all, we're going to quit making filtrate, which means we'll quit making urine, and that's a disaster, because what that'll mean is that nitrogenous wastes will begin to contaminate the blood rather quickly. An example of a condition in which the kidneys would shut down would be massive hemorrhaging, either internally or externally. The loss of the blood pressure due to the loss of blood to another cavity, either the outside world or inside the body, will result in a loss of net filtration pressure, and as a result, kidney failure and contamination of the blood. Okay, now we want to pick up here with filtration, the first process of cleaning the blood inside the nephrons of the kidney. Remember that we're going to deal with both hydrostatic pressure that comes from the beating action of the heart and osmotic pressure, which comes from dissolved solutes that are going to be present both in the blood plasma and in the filtrate. The colloid osmotic pressure in Bowman's is usually very close to zero, primarily due to the fact that the large protein molecules can't get through the filtration membrane and enter Bowman's and become part of the filtrate. But when you have conditions such as nephritis where the membrane is damaged, you can sometimes allow formed elements and large molecules to escape and enter the filtrate, and what this does is results in an increase in osmotic pressure. This will increase the volume of the filtrate, and this will also increase the GFR. High glomerular capillary pressure usually results from low resistance to blood flow in the afferent arterioles, which, remember, are going to be wider in diameter than in the efferent arterioles, and the low resistance to blood flow that happens in the glomerular capillaries. The high resistance to blood flow in the efferent arterioles, due to their small diameter, is what accounts for this bottleneck effect that jacks up the hydrostatic pressure in the glomerulus in general. And remember that we can control the degree of vasoconstriction, vasodilation of the afferents and the efferents as changes in systemic pressure occur from moment to moment. The pressure is lower in the peritubular capillaries downstream from the efferent arterioles. Filtrate, as a result, is forced across the filtration membrane at a net filtration pressure about 10 millimeters of mercury, and this forces the fluid into the peritubular capillaries from the interstitial fluid as well. Okay, so this is, again, what is desired in order to clean the blood and the interstitial fluid. Changes in the afferent and the efferent arterial diameter are going to change filtration pressure as we have changes in systemic pressure. Dilation of the afferent or constriction of the efferent is going to jack up glomerular filtration pressure. As a result, it'll increase GFR, and this will result in the production, obviously, of more filtrate and more urine. So how is it that we can regulate GFR? Autoregulation involves changes in the degree of constriction of the afferents As your systemic blood pressure rises, the afferents are going to constrict in order to bring the pressure down inside the glomerulus, right? Because if you've got more resistance to the blood flowing into the glomerulus, you're going to have less pressure in the glomerulus proper. The increased rate of blood flow of filtrate past the cells of the macula densa is a signal to the juxtaglomerular apparatus, causing the afferent arteriole to constrict. Now, this is kind of an interesting phenomenon. What we have to appreciate about the juxtaglomerular apparatus is that it's responsible for monitoring the osmolarity of the fluid in the distal convoluted tubule and making adjustments to the rate of blood filtration, reabsorption, and secretion all along the nephron. Essentially what happens when the macula densa senses an increase in osmolarity in the fluid in the DCT is that it's going to act to slow down the rate of filtration, production, and processing so that we can reabsorb the useful nutrients that we need to recover from the filtrate and we don't end up spilling them in the urine. So the increased rate of blood flow past the macula densa results in a signal to the JGM causing the afferent arteriole to constrict. And what this is going to do is it's going to slow down GFR, right? Because as the afferent arteriole constricts, the amount of filtrate we make is going to go down because the pressure inside the glomerulus is going to go down. And that results now in less urine production per unit time, but also more time to process the fluid that's in the filtrate. Under sympathetic stimulation, norepinephrine will constrict the small arterioles and afferent arterioles, and the result is going to be decreased renal flow and results in a lowering of GFR. And the purpose here is to increase blood pressure and blood volume so that we can provide oxygen and nutrients to the muscle tissue so that we can deal with our fight or flight situation. During shock or intense exercise, we have sympathetic stimulation and the rate of filtrate formation drops to just a few millimeters of mercury out of the glomerulus. And again, this is so that we supply the muscles with what they need in order to do their work. Tubular reabsorption occurs as the filtrate flows through the lumens of the proximal tubule, the loop, and the distal tubule, and the collecting ducts. And remember that reabsorption is essentially the rescue of useful solutes from the filtrate and loading them back into the blood. This results from diffusion, facilitated diffusion, active transport, symport, and osmosis. Remember that diffusion and facilitated diffusion are examples of passive transport, as honestly is osmosis to a degree, because that's simply the diffusion of water. Active transport and symport are examples of either the direct use of energy and ATP to drive the movement of solutes in whatever direction the cell desires, or the use of a gradient created by primary active transport to serve to power the movement of solutes against the concentration gradient in secondary active transport. Substances that are transported to the interstitial fluid and reabsorbed into the peritubular capillaries include inorganic salts, organic molecules, and 99% of the filtrate volume. These substances return to the general circulation through the venous system. If this didn't happen, we would lose so much fluid just through simple processing of the blood volume that we would dehydrate very, very quickly. So it's very important that we recover most of what we send into the kidney, or else we'd be in a bad way. In the proximal convoluted tubule, what we're faced with primarily is the recovery of useful solutes that enter the filtrate through the filtration membrane, which is part and parcel of the glomerulus. We have to get this stuff back because we need it, right? Substances that pass through the cells of the tubule wall, many of which have to be recovered, result from transport in the PCT. The apical surface is the portion of the cells that line the PCT that actually faces the filtrate, and this forms the apical membrane. Well, the basal surface faces the interstitial fluid, and this forms the basal membrane. The lateral surfaces are, of course, between the cells. And so what happens here? Well, we have active transport of sodium across the basal membrane from the cytoplasm into the interstitial fluid, linked to the reabsorption of most of the solutes. Because of active transport, the concentration of sodium is low inside the cell, and the sodium moves into the nephron from the filtrate through the apical membrane. Other substances moved by symport from the filtrate into the nephron cell are substances that should be retained by the body. So what we're doing is we're using this gradient created by pumping sodium to drive the movement of other critical solutes, mostly into the blood. Okay? Substances transported through the apical membrane include sodium, chloride, glucose, amino acids, and water. We need a lot of that. Through the basal membrane, we see a lot of sodium and potassium. Chloride, glucose, amino acids, and water all end up back in the eventually the venous return. Okay, so we don't want to lose that stuff, right? If we were to lose the bulk of our electrolytes or the bulk of our water or our nutrients in the form of glucose and amino acids, we'd be in a desperate situation. Here you can see a diagram showing you how the apical and the basal surfaces of the cells that line the PCT operate. So notice here that you've got sodium and chloride symport happening along the apical surface. Also notice that the apical surface has a lot of microvilli, right, to increase the surface area across which we have to do all of this biochemical work. Notice that we have symport of amino acids and glucose, and then we use some secondary active transport and facilitated diffusion in order to drive the amino acids, the glucose, and the potassium into the interstitial fluid, and then as a result back into the bloodstream. Okay, so just to revisit, remember that facilitated diffusion is diffusion that would not otherwise take place unless there were a channel protein that spans the membrane embedded in it. Polar molecules have to cross this way even if the gradient favors their movement. They can't get through the energy barrier represented by the plasma membrane the way that hydrophobic solutes can. Okay, so we need these transport proteins in order for facilitated diffusion to happen. Here you can see the symport operating. Okay, you can see again the movement of potassium along with other relevant solutes, chloride here in this case, back into the interstitial fluid, eventually to be recovered, of course, by the bloodstream. The number of carrier molecules is going to limit the rate at which we can move this stuff from the fluid in the PCT back into the blood. In diabetes, what happens is that due to the lack of sugar control in the body, either because the insulin signal isn't produced or the insulin signal isn't acknowledged in most cases, what happens is we overload the filtrate with glucose and we can't get all the glucose out of the filtrate and back into the blood, so some of it is going to remain in the tubule fluid. The high concentration of glucose in the plasma is reflected in the urine. This causes the fluid in the medulla to be drawn across the lining of the nephron into the filtrate. This increases the volume of the filtrate and it also increases the frequency of urination. Diffusion between the cells runs from the lumen of the nephron into the interstitial fluid, and it depends on the rate of transport of the same solutes through the cells of the tubule. Examples of solutes that move this way include potassium, calcium, and magnesium. The filtrate volume is reduced by 65% due to osmosis of water. That's, of course, going to follow these solutes primarily back into the blood. And again, we want to recover the vast majority of what enters the nephron Otherwise, we would dehydrate in very short order. The loop of Henle descends into the medulla. The interstitial fluid at this point is relatively high in solutes. The descending thin segment is permeable to water and moderately permeable to urea, sodium, and most other ions that can move across by passive diffusion. Water moves out of the nephron and solutes move in. So the osmolarity of the fluid as it descends into the medulla goes way up. We get about 1200 milliosmol by the time we actually hit the bend in the loop. Water moves out of the nephron, solutes move in. We reduce the volume of the filtrate another 15%. The ascending thin segment is not permeable to water, but it is permeable to solutes, which diffuse out of the tubule and into the dilute interstitial fluid. As the ascending limb heads back towards the cortex, we move into the thick limb. And what happens in the thick limb is that we actively pump sodium and chloride back across the tubule lining into the interstitial fluid, and there it establishes a salt concentration gradient in the medulla of the kidney. Okay, so the wall of the ascending limb of Henle is not water permeable, but it does actively pump the sodium across the wall of the basal membrane. This generates a concentration gradient for sodium, potassium, and chloride that are symported with the sodium across the apical membrane, and the ions pass by facilitated diffusion across the basal membrane of the tubule cells, and there they occupy the medulla. At the end of the loop, the inside of the nephron is 100 milliosmolar per kilogram. The interstitial fluid in the cortex is 300 milliosmolar per kilogram. So the filtrate within the DCT is much more dilute than the interstitial fluid which is surrounding it. Okay, and what's going to happen now in this last little portion of the trip is that we're going to adjust the fluid concentration of the filtrate so that we can reduce the urine volume to an optimum level. Okay, and that's controlled by the permeability of the collecting duct to water. Active transport of sodium out of the tubule cells and into the interstitial fluid with co-transport of chlorine is what's going to establish now the gradient in the medulla. Sodium moves from the filtrate into the tubule cells due to the concentration gradient. The collecting ducts extend from the cortex all the way through the medulla and empty through the papilla into the myocalyx. The water is going to move out by osmosis from the distal tubule and the collecting duct into the more concentrated interstitial fluid. But remember that the permeability of the wall of the distal tubule and the collecting ducts is controlled primarily by antidiuretic hormone secreted by the posterior pituitary gland. Urine can vary in concentration from low volume of high concentration to high volume of low concentration. And again, this is in order to maintain our fluid balance. We don't want to lose fluid or electrolytes unnecessarily. At the same time, we don't want to accumulate fluid unnecessarily. And that's why the kidney can adjust on the fly the amount of urine it actually produces. Urea is going to enter the glomerular filtrate. As the volume of filtrate drops, the concentration of urea will go up. The walls of the nephron are not very permeable to urea, so only about 50% is passively reabsorbed. Urate, creatinine, sulfates, phosphates, and nitrates are partially reabsorbed, so the concentration is high in the urine. These are toxic substances that need to be eliminated. Another thing we should point out about the urea in the medulla of the kidney is it does also contribute to the medullary concentration gradient. So it's part of what's responsible for pulling the water out of the DCT and the collecting duct on its trip ultimately to the myocalyx of the kidney. Tubular secretion is the movement of toxins out of the plasma and interstitial fluid and into the filtrate. So metabolic byproducts, drugs, and molecules that are not normally produced by the body are moved into the tubule of the nephron either actively or passively. Ammonia is made by epithelial cells of the nephron from deamination of amino acids, and it diffuses into the lumen. This is a very toxic compound because it is a powerful base. If it were allowed to accumulate significantly in the plasma and in the tissue fluid, it would cause the pH to rise to dangerous levels. Protons, potassium, penicillin, and substances like PAH are actively secreted into the nephron as well, and then eliminated in the urine stream. So here we can see how we control secretion of hydrogen and potassium. This is critical not only for electrolyte balance, but also to maintain the body's pH at close to neutral in most body compartments. So we see here in part A, all right, if we look, hydrogen ions are secreted into the filtrate by countertransport in the proximal tubule. Okay, so this is looking at here the movement of the filtrate in, and you can see here the movement of solutes across the tubule lumen. Okay, so here we're seeing secretion of protons into the fluid. Protons either diffuse from the peritubular capillaries into the interstitial fluid and then into the epithelial cells of the tubule, or derive from a reaction between CO2 and water in the cells of the tubule. Sodium and bicarbonate anion are transported across the basal membrane into the interstitial fluid, and they diffuse into the peritubular capillaries. Next, we have protons and potassium secreted into the filtrate by countertransport into the distal tubule. Sodium and potassium move across by active transport across the basal membrane, while sodium and bicarbonate are co-transported across the basal membrane into the interstitial fluid. Then they diffuse into the peritubular capillaries. Now, you might well ask, okay, that's all well and good. We can control the amount of proton that we put into the filtrate, and ultimately that ends up in the urine. But how do we avoid damaging the distal convoluted tubule and the collecting duct as a result of the accumulation of protons that's obviously going to perturb the pH in the filtrate? And the answer is that there's a lot of buffering that goes on in the filtrate as well. The phosphate buffer system, for instance, is important in regulating the pH of the filtrate and, by extension, the urine, and this avoids the damage that would otherwise occur through wild swings in pH that wouldn't be tolerated by the tissues that line the nephron. This is one of the reasons why if you consume acidic foods, you tend to generate a urine that's going to have a lower pH. If you consume basic foods, you're going to secrete a urine that's higher in pH, but not dramatically so, because of the buffering activity that goes on in the filtrate and in the urine itself. Okay, that brings this portion of the talk to an end. I'll see everybody in class, and have a good night.